This is FRM Part 1, Book 2, Quantitative Analysis, and the chapter on stationary time series. We've spent some good time talking about cycles. Remember, we had a business cycle, we had an operating cycle. There is seasonality, there are weather patterns, there are all sorts of repetitive behavior. Remember, the idea is to determine whether or not history repeats itself. And we, of course, know that history repeats itself. This happens all the time, but the question becomes, to what degree does history repeat itself? Lots of events that occur in personal lives and in public lives and in stock markets and in bond markets where people look at it and say, oh yeah, I should have been able to predict that. But the question then becomes, how perfectly does history predict the future? And so what we're trying to do is find these cycles and see if these cycles can't help us in our risk management principles. So let's look at these learning objectives for this chapter. We're going to define and describe a whole bunch of terms like covariance stationarity, autocovariance. Notice a lot of these words have auto in front of them. I'll explain that in just a little bit. Covariance stationary, that's really an important concept, which leads us into white noise and lag operators and the general linear process. And then we're going to calculate some statistics. So let's get to it. Let me just remind you about a time series. This is an ordered sequence of values of a variable at equally spaced time intervals. And those time intervals, they could be a day, they could be a week, they could be a month, or any other time period. 20 years or so ago, that interval was chopped down to maybe 10 seconds or a second when day trading became really popular. One of the variables is independent, and the second is a dependent variable, just like we've been doing for the last couple of chapters. One good example is a graph of U.S. GDP growth rate in the last 50 years. And so time series can help us with economic forecasting and sales forecasting, and it can help us try to predict all different types of stock market data, and it helps us with budgets as well. Time series can be divided or decomposed into a couple of different parts here: a trend component, a seasonal component, a cyclical component, and then a random component. And as you might guess, we're going to focus on that third component in this chapter. Let's start with autoregression. Let me define an autoregressive model as a time series model that uses observations from previous time steps as inputs. And then the idea is to predict the value at the next time step. Consider someone who's trying to predict the temperature today in a particular state in the United States. Well, what's the best measure of the temperature today is probably yesterday's temperature. Over time, not on a daily basis, but over time that averages out. And then maybe the day before and the day before. But notice you get into seasonality and cycles and little ice ages and all the stuff that goes on with the climate. So those values are known as lagged values. So look at this time series. We have X, which could be the stock price of any particular company or the S&P 500 index, or it could be sales or labor participation rate. And so we're saying that that's a function of last period's variable plus the period before, plus the period before, plus the period before. And you can have, I guess theoretically you could have tens of lagged values, maybe hundreds, I don't know, thousands. That doesn't make a whole lot of sense. But I'm sure there's somebody out there who's lagged it 1,000 times. How about the example I have at the bottom of the page? U.S. GDP this year might be a function of GDP figures over the last 10 years. And, those of you who have a little bit of an economics background, or at least follow the size of the U.S. economy, every year the U.S. economy gets just a little bit bigger, a little bit bigger, a little bit bigger. Sometimes it contracts. We call that a recession. So think about this time series with GDP. You have generally rates of increase in this value of 1% or 2%. Oh boy, in the 80s we had 4 and 5%. In the 90s we had a 5%. I think this last quarter here in 2019 was over 3%. But then you have periods where the economy contracts by 0.5% or 1%. So think about trying to predict future GDP based on that history. We're trying to identify patterns, not perfect patterns like I said in the beginning, but we're trying to identify enough patterns to help us predict the future. Here's this important term, covariance stationarity. So let me give you just a quick example here. Let's suppose we're tossing a coin, right? And we can have either 1 for heads and 0 for tails. And we do this, tens of times or thousands of times. And so let's ask the question, what is the probability that the value of the time series will be equal to 1 at some time, like maybe the next flip, or maybe the 15th next flip, or the 100th next flip? All right, if the same coin is being tossed, and remember, this is not one of those Ocean's 8 or 9 or 10 or 11 movies where the coin is manufactured so it always hits tails or something, or in a James Bond movie. But let's suppose we have that equal probability of a head or a tail. So the probability of tossing a tail at the time t plus 1 is the same as the probability at tossing a tail at all times, t plus 2 and t plus 8 and t plus 400, because with a fair coin and a fair thumb, a fair flipping of the thumb and then a fair landing spot, of course, those probabilities are always going to be the same. All right, so this is the idea behind covariance stationarity. So by assuming that future probabilities are the same as historical probabilities, we're able to use that sample data, that sample information, to draw inferences about those probabilities. All right, more formally, time series is covariance stationary if all of the terms of the sequence have the same mean. And if the covariance, there's where we get that term, the covariance between any of those two terms in the sequence depends only on the relative position of those two terms. Look at my little timeline there. The relative position, not between like I and O or P and K, but their relative, not their absolute position. Now, here's the important part of this. In order to conduct a valid statistical inference based on an autoregressive model, in other words, in order to be able to say, okay, I believe that GDP in 2020 is going to be $24 trillion, and stand by that and say, by golly, I'm pretty sure that's going to be an accurate prediction. Well, we have to assume covariance stationary time series. Now, even more formally, but in more detail here, 3 basic requirements. So the expected value of a time series must be constant and finite. The variance of the time series must be constant and finite. And the covariance of the time series with itself over a fixed number of periods must be constant and finite. Now, here's the important thing. If a time series has a trend line, like this GDP growth that I've just been talking about, it's growing and growing and growing and growing, or the labor participation rate, I think we had some good graphs in previous chapters about that. By definition, that time series it cannot be covariance stationary. All right, some other terms to know: autocovariance function and the autocorrelation function. Let me start with autocorrelation. What that does is, it has the word correlation, so everything that we've learned about correlation applies here, but the auto term means that it's kind of automatically against itself from some kind of a lag period. So look at that second circle point I have there. Has much to do with the correlation of time series observations with the previous lags, all right? And so we're looking at the interdependency between data points in a time series. Now, the autocovariance function is a tool that's used to quantify the stability of this covariance structure. And there are lots of software packages that will enable you to use that autocovariance function. And what it does is it helps you identify and summarize and and maybe even analyze some kind of dynamic relationship in a time series that could be cyclical. Here's a good picture of some autocorrelations. Notice correlations go from 0 to 1 up on the vertical axis, although we do have a little bit of a minus 0.2 on the bottom. I guess we could go all the way down to a minus 0.1, right? Correlations have to be in that range. And then the lags go from 0 all the way out to some big number. And notice that, you know, the first and the second lag, those are relatively dependent, but then that just kind of tapers off as you get lagged variables all the way out to 50 lags. And if that's 50 months or 50 years, especially if it's a longer term, like a year, you know, what does the GDP in 2020 have to do with the GDP back in, oh wow, 1970? I was even alive in 1970. You know, so you get the sense that, of course, that it's reasonable to assume that the farther back you go, the less influence that's going to have on today. I mean, we talked about this back when we did things like reversion to the mean, and a big finance question is the stability of beta, whether beta is stable over time. It depends on over what time period that you estimate that beta. How about partial autocorrelations? I mean, this is really a cool concept in the fact that, you know, think about it. You got this time series, right? And so you're trying to establish the relationship between the xt and then xt minus 1 and t minus 2 and t minus 3. Suppose that you lop some of those variables out. What happens? Well, that's what partial autocorrelation is. And so look at my second circle point there. Partial autocorrelation at lag k is the correlation that results after removing the effects of any correlations due to the terms at the shorter lags. You know, so partial autocorrelation at lag 20 is the correlation between observations that are 20 steps apart, but you remove all the stuff in between there. And of course, you know, you would pick 20 because it has some kind of economic or practical significance that can be supported by some form of a theory. And so you can have positive and negative correlations. White noise. How about this concept? First time I ever heard about noise was an article written by the great Fisher Black, and it was the shortest title of any academic journal article ever published in the top finance journals. It was just called Noise, and it was really a fascinating article. But so white noise, as it applies here, really has very little to do with what Fisher Black was talking about, but some. White noise is a time series, but has a couple of really cool characteristics. It has a zero mean, it has a constant variance, and it has no serial or autocorrelations. And so inside the blue box, there's the formal definition of a white noise process. The expected value of the time series, the y sub t, is 0 for all t. Expected value is 0. The variance is fixed at that sigma squared, and notice there, on the far right, it's less than infinity, which that's the mathematician's way of saying that it has to be finite, and then the covariance has to be 0. Now remember what we're trying to do here. We're using these models to try to predict something, but the data can never be perfectly described by a model. So there's going to be some error. Remember, I always talk about this error term. Sometimes it's called a disturbance term, but that error term is going to be the white noise. And there's a picture of white noise. So we have time going along the horizontal axis, and then some dependent variable going up the vertical axis, starting at a -3 all the way up to 2. And so there's that function, and so we can observe all of those functions over those, 42 or 43 time periods. And then we can compute the autocorrelations down at the bottom, and those autocorrelations, show the spikes going up and down, and you can see that even with the spikes, there's no autocorrelations greater than 0.2. So this white noise, so let me go back here. So expected value is 0. I mean, what does that look like? If you just kind of draw a line right through, is that line horizontal? Probably. How about a constant variance? Well, if you look at, the ranges here, I mean, it's hard to predict variances because it's a squared term, but a constant variance, I mean, it sure looks like it is. And then you really can't tell what the covariances. You got to get out your Excel or some other model to calculate those. But clearly this looks like white noise. Now, it can be zero white noise, and this is the notation in that top light blue box that the time series Y is zero mean white noise. That's inside the parentheses, the mean and variance. Now, if Y is both uncorrelated and independent, then we throw those three letters up there, IID, identically and independently distributed. And then if it follows a normal distribution, we call it a normal white noise or Gaussian white noise. How about these characteristics? And so this is what I've just been talking about here for several minutes. Unconditional mean and variance must be constant for any covariance stationary process. All right. The lack of any correlation in a white noise means that all autocovariances and autocorrelations are zero. And then both conditional and unconditional means and variances are the same for an independent white noise process. Now, why is this really important? Why do we spend a few minutes on this? This is really important. If a time series is a white noise process, then by definition it is random. And what does that mean? Random means that I've used my children as examples in some of these videos. I like to suggest that their performance on their German tests is random. So what does that mean? We cannot predict. It doesn't matter how many times they study. It doesn't matter how many hours they study. Their grades could be really high or really low. I mean, that's not true, of course, from a statistical standpoint. But from a parenting standpoint, it sure seems that. So if it's random, if it's white noise, it cannot reasonably modeled for purposes of prediction. So we need to test to see if our time series is white noise, and if it turns out to be white noise, then we can just throw it there on the page and say, okay, it's white noise, let's try to do something else. Now, how do we do this model diagnostic? So once predictions have been made by a time series forecast model, they can be collected and analyzed. If the series of forecasted errors are white noise, now the forecasted errors are white noise, it means the model has succeeded in harnessing all the vital information, and all that's left is random fluctuation. If not, then the model may have to be improved. How about lag operators? This quantifies how a time series evolves by lagging a data series. All right, so there in the first light blue box, we're going to use that notation of the lagged operator of the time series is equal to the time series back by one time increment. And it could be 2 time increments there in the middle box, or it could be k time increments. Let's go ahead and start with the definition of a moving average. And so this is a popular method to model time series. Establishes a linear relationship. All right, so we're going back to simple linear regression and multiple regression, some of those same kinds of concepts, to establish a relationship between an output variable and current and past values of a stochastic term. And remember that stochastic term is not able to be predicted. All right, so in these basic terms, an MA model is a linear regression of the current value of the time series against previous observed white noise error terms. All right, so here's the model. This is called a first order moving average process. So on the left-hand side of the equal sign, there's our time series, and we have those white noise terms there. So we have the white noise at time period t, which is the current time period, and then the white noise at time period t minus 1. And that t minus 1 white noise variable is going to be influenced by a coefficient. And so note that those terms are defined there. There's the current white noise shock. We're calling that a shock because remember, that the expected value of the white noise, the mean of white noise, is always 0, and it has a constant variance. And by the way, I remember back in my PhD classroom days, the professor would sometimes describe white noise and say things like, well, it has a mean of 0. And then sometimes he would not say that it has a mean of 0. So I remember thinking, well, maybe sometimes it does, maybe sometimes it doesn't. But in fact, it does. All white noise processes will have a mean of 0. Has a lot to do with the finite power processes and spectral density, if you guys remember that stuff from your old time math days. But anyway, just remember that that has a finite variance, and it has a finite and constant variance, and a constant mean, which is going to be 0. And so the number 1, that moving average parentheses 1, means that it's a lag of just 1 step, which of course means that we could probably go back more than 1 step. We'll do that here in just a minute. But first, let's take a look at an example. And this moving average process has lots of good applications. Of course, as a financial risk manager, you're trying to do things like predict what's going to happen at the next step. Like maybe what's the stock price going to be tomorrow? What's the bond price going to be tomorrow? What's the price of the credit default swap going to be tomorrow? So it has lots of good finance and financial risk management applications, but also has lots of economic applications in terms of trying to figure out, what's going to happen tomorrow. Like in this example, daily demand for fans that is going to depend on the outside temperature. I did read a really fascinating application of the moving average process. Let me just take 10 seconds here to say this to you. I recently had an MRI on my neck because I got this big bulge in my neck and pain going down my left side. But an MRI and a CAT scan is essentially a picture of your spine, taken at, pretty quick intervals. And so it goes up your spine and goes up your spine. And so you can use this moving average to predict what the next picture is going to look like for your spine. I'm sure you guys don't care about the bulge in my neck. Anyway, so here's an example. Daily demand for fans. We have that demand on the left-hand side of the equal sign, and then the 2 white noise terms on the right-hand side, and they're adjusted by a demand factor of 0.2. So here's some really cool applications and implications and inferences that we can make based on this, what looks like really a simple model. And so if we're using only the current period's error term, then the daily change in temperature is positive. If it is positive, then the daily demands would also be positive. And so that makes sense. I mean, if the temperature today is 90 and then the temperature tomorrow is 95, that must mean that, hey, that makes some sense that demand would be positive as well. And then if we go back to 2 days ago or 1 day ago, if that error term is also positive, then we would expect, and notice I love this, I love the way this is termed, an amplified impact on our daily demand for fans by a factor of 2. And so that makes perfect sense too. I mean, if the temperature is, let's say 88 and then 92 and then 95 and then 105, you amplify that. I mean, you think about, okay, the temperature can't stay hot forever. And then the next day it's 95 and you think, oh, I'll just hang on for 1 more day. And then it's 98. You're hanging on, and sooner or later you say, oh, I got to do that. So there are people that buy fans when it's 80 degrees and then people that buy fans when it's 95 degrees. And so somehow this model captures that. Here are some properties. The unconditional mean is 0, which should make perfect sense based on our white noise conversations from before. The unconditional variance then has to be a function of that theta, which is, here, let me just go back here really quickly. There's that theta. And by the way, we're going to be tempted to use, just our regular linear regression, ordinary least squares to estimate that, but it gets a little bit more complex. I'll tell you about that in just a second. So what was I saying here? That unconditional variance then has to be a function of that theta. And there it's broken down into its parts in the middle blue box. Conditional variance then is just sigma squared, of course, and remember that's conditional on all of the white noise terms from, epsilon sub t all the way back to t minus 1 and t minus 2. Now, there's this concept of inversion that's pretty important here. Here's the thing. Remember that any stationary moving average process can be expressed as an autoregressive infinite process that we talked about just briefly here a second ago. But if that theta term is less than 1, absolute value of it is less than 1, then the infinite time series process then converges to a finite value. And then we say that it can be inverted. And that's important here. And so we're inverting it, and so that's what we're doing in that blue box there. This is referred to as the autoregressive representation. There's that infinite process that I was talking about just a second ago. So look at that first circle point there. This process of inversion enables the forecaster to express current observables in terms of past observables. So my children have this German test today. So whatever they perform today can be explained by their performance in the past. And there's that last block point. Absolute value has to be less than 1. Now, of course, as I said before, we don't have to just limit ourselves to going back just one period. We can go back way, way as far as we want. And this has greater applications. I remember sitting in that, actually I was laying in that tube for my MRI on my neck, and I was in there for probably 45 seconds. And those of you that have had an MRI, you know that there's a lot of banging going on. Boom, 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 boom. So I really don't know what's going on there, but it sounds to me like in trying to apply this to a time series that they're taking pictures, every second or every half a second or every 2 seconds, whatever it is. And so, boy, in 45 minutes, how many seconds are there in 45 minutes? I really don't want to do the math very quickly, but you can imagine that you might want to go back to the beginning, that first picture of the first part of my spine, maybe down here to get all the way up here. I don't really know what I'm talking about with science, but it makes some sense. And so notice those are the white noise error terms. And so this MAQ, Q stands for this generalized representation of the MA1. And so you can go back all the way as far as you really want to. So it's important to remember, look at the third block point, that the MAQ and the MA1 process are similar in all aspects. Now, look at the last one here. When Q is greater than 1, that lag operator polynomial will have Q roots. But there is a chance that you could get some of those complex roots. Remember, when do you learn about complex roots and imaginary numbers? I remember thinking these mathematicians, these men and women are so smart to come up with something. What is the square root of a -1? Oh my gosh. All right, so here's some of the properties. We know that it's covariant stationary. We talked about the invertible mean. We talked about the invertible process. The conditional mean depends on the first lag if it's an MA1, and where if it's an MAQ, it's going to depend on all of those other lags. And then here's an important one, this fourth one, the autocorrelation functions. So that if in the MA1 case, all the autocorrelations beyond 1 are going to be 0, and then beyond Q in the MAQ one, those are going to be 0. I do remember back in my graduate days, we used Excel and we did all this stuff, and sure enough, I remember it was kind of like magic. They all came out to be 0. All right, how about swinging back to the AR model? And so there's the time series on the left, and on the right-hand side of the equal sign are those previous values of that time series, and they're all going to be weighted by some coefficient. Okay. Now, this AR1 is an autoregressive process where the current value, YT, is based on the immediately preceding value plus some error term. And that error term is going to be white noise. And a lot of people think of it as a shock. Remember, if the mean is 0, then the only thing that can happen is of interest. I mean, think about a mean of 0. Let me just draw a line here like this. Think about a mean of 0, and you got a bunch of values that are a little bit above and a little bit below, and they kind of cancel each other out. But suppose you got one way up here or way down here. And so lots of researchers interpret that as a shock, like a shock to stock prices, or a shock to credit default swap prices, or a shock to a credit rating. And that theta is the coefficient of the process at time t minus 1. All right, so that last block point, let's look at just a GDP growth series. Since we've done this in some previous chapters, the autoregressive model AR1 is going to use only the information on GDP observed in the last quarter to predict that next quarter. Now, once again, we're probably tempted to use some kind of an ordinary least squares model to estimate that coefficient. But it's probably not going to be as easy as that. And I'll talk about that here in just a second. So here are the properties of an AR1 process. The AR1 process is covariance stationary only if theta is less than 1. The autoregressive process is always invertible, unlike the MA1 process, which relies on theta being less than 1. There's the unconditional mean of 0. There's the unconditional variance. And there are the conditional mean and variances as well. All right, so here, getting back to this process of, can we use that regular old OLS? And the answer is probably not. So to estimate those autoregressive parameters, such as theta, we're going to need this Yule-Walker process. Now, what Yule-Walker is going to do, it's going to help us determine the entire autocovariance sequence, which means that for any value that we have today, that we're going to be able to predict that value tomorrow. Let me show you what that means here just mathematically. So if we begin with an AR1 model there in the top light blue box, and then we're going to play one of these math tricks. I remember learning this back in, I don't know, maybe 7th grade, where my 7th grade math teacher said, hey, let's multiply both sides of the equal sign by some number, and it doesn't change the equal sign. But what it does is it allows us as 7th grade math students to work down and find some other kind of a result that has maybe some application to something else. So I remember thinking that multiplying both sides of the equal sign by the same thing is really a cool part of mathematics. And so all we're going to do is multiply both sides by the time series at time t minus tau. All right, and so we get that middle, little bit darker blue box. And then if we assume that tau is greater than or equal to 1, and we take the expectations of both sides, we get that gamma tau is equal to, there's our theta, and all we're doing is kind of doing some factoring there. And that's the Yule-Walker equation that we're going to use to estimate theta. And notice that's a little bit different than just using ordinary least squares. All right, so when we're going to do this, we're solving for these autocorrelations. Remember, the autocorrelations are just the correlation between the sequential error terms. And so we're going to use that following relationship where rho at time t is equal to theta raised to the t. And if we do this using some software, we maybe get a result like this where theta is equal to 0.7. And so using this concept derived from the Yule-Walker equation, that first period autocorrelation is going to be the 0.7. The second period is going to be 0.7 squared, and then 0.7, and so on as we go through those final autocorrelations. Now here's the general pth order of the autoregressive process. And so all we're doing is taking my children's performance on their last German test and their performance on their second to last German test and third, and et cetera, et cetera. And so notice that error term at the far right is white noise. This process is going to be covariance stationary, and it's going to behave similarly that we found. Those autocorrelations are going to behave similarly as in the AR1 process. Now, how about if we combine the moving average and the autoregressive models to obtain a better approximation of that Wold representation that we discussed. Now, remember what this dude Wold said is that every covariance stationary time series is really the sum of two time series, one that's deterministic and one that is stochastic. So what we can do is we can throw the AR and the MA into a time series model so that we can get the subtleties of each model to be able to predict better, accurately predict and make inferences from that time series. Now, the reason that this is so important is that this is going to be a great model for time series that show signs of seasonality. Now remember that seasonality is most apparent when those autocorrelations for a data series do not abruptly cut off, but rather decay gradually, and then every time there might be a periodic spike. And I do remember looking at my Excel spreadsheet back when I was in graduate school, and we could see these autocorrelations, and they would just fall by a little bit, or around the same amounts, and then all of a sudden there would be something different in there. And so that's what's happening with this model. So let's take a final example here. There are some observable variables of a time series. Let's suppose that it's Gaussian white noise. And we're just going to use our regular old moving average 1 model and substitute those values in there. And so that time series in time period t is going to be 058 based on all the stuff that we've talked about during this chapter. All right, what we're probably going to want to do at some point is test whether or not these groups of autocorrelations are going to be statistically different from 0. We can do this with the Box-Pierce Q-statistic or the Ljung-Box Q-statistic. And notice that the formulas are very similar. You've got the autocorrelations squared, and we're summing them from t equals 1 all the way back to however many lags we have in the time series. And then notice what we're doing. We're essentially adjusting for something that's kind of similar to the number of observations and the degrees of freedom. And so these are really just two ways to test the null hypothesis that the time series is white noise. And this is going to follow a chi-square distribution. So let's take a look at a final example. Suppose we have 300 data points and we've got a lag of 1, 2, and 3. There are the coefficients. And so the question asks us, according to that learning objective, to compute the BP statistic and the LB statistic. And so I'll give you a moment just to kind of toggle back and forth between that formula there and what I have on the slide there, so you can kind of get a sense of what we're doing in terms of these calculations. And one cool thing about these two tests is if there's a large enough observation that these two tests generally produce pretty similar results. And remember, this is chi-square, so boy, the difference between the 22.5 and the 22.74 probably not going to have a critical value from the table to fall in between those. Now, of course, you got to be concerned when the number of data points is relatively low, like 5 or 10 or 15. And that takes us through